Right.
Yeah, do you remember? That's one of the tools in your arsenal. In fact, we now have a pretty rounded out arsenal. What we're going to be doing today is now using it to solve some interesting problems, like how do you compute capacitance instead of just having the instructor give it to you the first week of class? I know, but that's we now have a very powerful arsenal with which to attack electrostatic problems. Here's our arsenal, right? We have charge. Well, let me start off with the fundamental qualities or quantities that we're studying. Charge, and we can represent that with Q or rho sub S or rho sub L or rho sub V. Lots of different ways. Volume, line, surface, or point charges. And those are always in coulombs, coulombs per meter squared, coulombs per meter cubed, coulombs per meter cubed. Another thing that we want is E field. We represent that with a vector. And that's volts per meter. Another thing that we like to look at is D field, or electric flux density vector. That's a vector field. It has units of coulombs per meter squared. And let's see, finally, we also studied last week what a voltage was. We gave a formal definition. It has units of volts. So really, all of electrostatics is just sort of manipulating these quantities to analyze problems. And in fact, you now have a sort of a tool set so that, for example, if you want E field and you have charge, you use Coulomb's law. And of course, recall that Coulomb's law is the volume integration of whatever charge density as a function of a variable of integration r prime times r minus r prime dv prime, integration over the volume, and then you got to divide by 4 pi epsilon magnitude cubed. That vector cubed. And this will tell you what the E field is. That was the first electrostatic lecture. We learned last week, of course, you can, if you have charge and you want voltage, you use your voltage integral. And that looks similar to this one, except it's completely scalar. Because remember, voltage is a scalar. And the other thing is that it was only a magnitude r point of observation minus variable of integration to the first power, not the third power in the denominator. And we just had scalar voltage, or scalar charge volume density as a function of our variable of integration. That was our second tool in the arsenal.
Did you say we want half backwards for that, or write it backwards?
Did I write something backwards?
Well, you said if you want charge and have...
If you have charge and you want voltage, you put your charge in that integral and it gives you the voltage. So voltage is equal to, E field is equal to, E field as a function of R vector. Now, if you have E field, and you want the D field, the electric flux density, we call this the E field in electrical engineering. There's actually a standards body in IEEE that says, what should we call things? And it's actually different than what the physicists call things. That is electric field. That's it. You'll see like some old times books and stuff call it like the electric field strength, or something like that. And there's some non-standard usages. We call that the electric field. Nothing more, nothing less. And if you've got this and you want this, in this class, the only thing you have to worry about is this simple material relationship. D is equal to epsilon times E. Epsilon is a constant. We talked about the physical meaning of that. It's the stretchiness of the electrostatic molecules inside of a material. You impress an E field. It makes the electrons go one way. It pushes the positive nucleus the other way. And that makes a countervailing E field that suppresses the total E field for the same given charge flux density through a material. And that makes E look a lot smaller than D proportionately when you start adding stuff. Yeah?
When do you use epsilon naught and when do you use epsilon?
Oh, okay. So epsilon naught is when you're in free space, right? Or air. Most of the problems we work in electromagnetics, they're in the world we live in. It's either going to be in outer space or it's going to be in air. And so a lot of times you'll see me just write epsilon naught. If you want to, you can, in these particular relationships, it's okay to put in epsilon, where you assume that there's a homogeneous medium present that has this permittivity. Now, there's a little caveat here, and we're not going to get into problems this difficult in this class, but when you have an inhomogeneous material, like say half of your space is epsilon, the other half is epsilon naught, that's a trickier problem. We won't be dealing with any of them quite like that here, but I can kind of give you a feel for what setting up a problem like that looks like. Good question. So I say this is a constant in this class. If you get into higher level EM theory, first of all, this can be nonlinear. It can be a function of the magnitude of the E field that you're impressing upon it. There's some materials that behave like that. Another thing this can be is a matrix, a 3x3 matrix that multiplies a 3-element vector, x, y, and z, and gives you a 3-element vector, x, y, and z. It turns out you need to turn this into a matrix when you described how the E field in radio waves propagates in the ionosphere of the Earth. And the whole reason why that happens is because the ionosphere has charges in it, and there's also a magnetic field present, the Earth's static DC magnetic field. And it turns out those two together will make something called an anisotropic medium, which is best represented by a matrix. Does that encourage you to study higher level EM theory?
Sure.
Yeah, sure. Okay, good. I like it. I like to have a gung-ho class that's not scared off by stuff like that. Anisotropic media are very difficult to deal with analytically. That's for very big boys and girls, which I'm sure you'd be if you continued on in the class. So let's see, another thing. If you have the D field and you want the charge, you want to undo Coulomb's relationship, you have E or D, well, we can switch between those easily, and you want to undo the charge, or the field solution, and figure out what is the charge that made that field. What relationship do you use? Gauss's law in differential form. That's the really nice one. Gauss's law of differential form. You can use the integral form too, but this is so much easier to remember. Rho sub v is equal to the divergence of your electric flux density vector. What does divergence really mean in geometrical terms? Sourciness. That's right. Let's see. What's another one we can do? Anything else that we learned? Oh, well, you did learn a couple. Hopefully the one that stuck in your mind was last time was a combination of rules. Oh, let me start with this one. When we defined voltage, if you have voltage and you want the E field, This is the scalar electric potential. This is your E field. These are basically the definition of voltage and electric field, and that is that voltage, if you take the gradient with a minus sign in front of it, becomes your E field. So you take your scalar electric potential, you take the gradient, that tells you sort of the steepiness, the gradient, the direction, the sharpiness. You can invent your own thing for this. As much as important as the math is, it's equally important to get a geometrical understanding of what this stuff does. And so this is basically, E field is going to point downhill, the rate of steepest descent in this voltage function as a function of space. And so that's going to tell you where those electrons are going to be, or where the protons are going to be forced. Electrons always travel opposite the electric field. And now, Laplace's equation last time was actually the combination of a couple of these relationships. So, for example, if you take a look at this, let's plug in some stuff. Minus the gradient of voltage is equal to the E field, which of course is going to be equal to 1 over epsilon, the D field. So I got a vector here, because anytime I take the gradient of a voltage, I get a vector. And I got a vector over here, because that's the electric flux density in coulombs per meter cubed, squared, excuse me. And so what I'm going to do is I'm going to take the divergence of both sides. Now remember, this is a constant in this class, so I can take my divergence operation straight on through. And I noticed that this is actually, I have a relationship, Gauss's law in differential form, that can just replace this. This is the volume charge density at a point in space. So if I rearrange this, this is called Poisson's equation. It's actually just a rearranging of stuff you already know. And in fact, in a charge-free region, this is 0. So we say that the divergence of the gradient of V is equal to 0. When it's in this form, we call it Laplace's equation. Special case of Poisson's equation in electrostatics. Now, this is where it gets a little hairy. The divergence of a gradient happens a lot in vector calculus. And so we have our own little special symbol for that operation. It's actually nabla squared. You take the del operator and you put a 2 up at the superscript. And that means the same thing as taking the divergence of the gradient of something. If I wanted to write this out longhand, you see how elegant this is, because it saves us from a lot of tedious mathematics. Let me go over and just write this out longhand just to prove how much simpler this is. If this is equal to the divergence of the gradient of V, well, what is the gradient of V equal to? It's equal to partial derivative with respect to x of the voltage. Stick it on the x hat component. Partial derivative with respect to y. Stick it on the y hat. Partial derivative of v with respect to z. Stick it on the z hat. And then the divergence operator, which treats, of course, this thing like another differential operator here. Partial derivative with respect to x, stick it on the x. Partial derivative with respect to y, stick it on the y. Partial derivative with respect to z, stick it on the z hat. this vector gets dotted into that vector to construct our final operation. So the x components, you got to go together. And remember, when I dot a vector with a vector, I get a scalar. I'm just multiplying these two components, adding the product of these two components, adding the product of these two components. And what I'm left off with is second partial derivative with respect to x of voltage plus second partial derivative with respect to y of voltage, plus second partial derivative of voltage with respect to z. And of course, this was a very tedious analysis. You don't ever have to, this is the only time you ever have to write it out longhand again. All you have to do now from here on is just use a super cool person electromagnetics terminology. And this operation is called the Laplacian. This is way cooler than the Laplace transform. I remember the first time I ever taught this in this class, I put the word, I didn't even say it, I was introducing the lecture, and I wrote the word Laplace on the top of the board. And I heard the most despondent sigh come out of the class as soon as I had done that. Like, what are they doing to you in 2025 that make you hate this man Laplace so much? Do they make you do the transforms in 2020? Is that where you learned that? Diffie-Q? Oh, good. Ooh, good. That's a great tool for solving differential equations. So anyway, this is the Laplacian. So back over to Laplace's equation. Whether you write it out like this or longhand, it's a fairly simple equation. It basically says that partial derivative with respect to v, the components with respect to x of v with respect to x, y, and z, second partial derivatives, all those things, always going to add up to 0 if there's no charge present. Did you work through any, does this sound anything like the lecture from last Tuesday? Yeah. Then did Dr. P derive the voltage with respect to a two-dimensional problem? You do any numerical work? Yeah. So it turns out, like, especially in like 2 dimensions, they probably worked in 2 dimensions here. This equation is really quite simple. It looks kind of complicated because it's a differential operator. But hopefully what you saw is that when you discretize voltage in space into a grid where this delta y is the same height as the delta x, you know, if you want to basically computer model this thing, you gotta represent this continuous space-varying voltage function as some sort of matrix, right? That's the only thing computers do, discrete point calculations. So how do you do that? You bust the world up into a matrix, into a grid, and take samples of that value in 2D. And hopefully what you saw is that even though this looks really complicated, when you digitize this, what you can show is that the voltage here at this node is really just the average of its neighbors. You did that?
Yeah.
And did you step through a little example that had like a square box and you solved your first boundary? This is your first foray into numerical electromagnetics. Do you know that? We let the master teach you. Dr. Peterson is kind of one of the world's most famous researchers in that field. Probably published the quintessential textbook in numerical electromagnetics. And this was your first exposure to it. You learned it in electrostatics. This really isn't that hard. In fact, you can even set up a spreadsheet to solve EMAG boundary volume problems of this type. You make a cell, block off a cell that represents your place in space. You can put the boundary values all around. And then you can solve for the internal voltages by just making a rule in your spreadsheet. This cell is the sum of all the adjacent cells, averaged together. And then just cut and paste that formula throughout the entire grid. And then voila, if your Excel doesn't hiccup on the fact that you've got all these dependent references in it, it should produce the solution in a matter of moments. You can do it in MATLAB really easily too. In fact, I have made some code that allows you to do that in MATLAB, and that will be the crux of your homework number 9 assignment, which will be posted today. It is. And it's so cool. Randy, it's so cool. You're actually going to be able to solve real value problem. boundary value problems. Not just this silly square stuff, but things that correspond to transmission line topologies.
That's what I'm talking about.
This is my favorite student now. Who was my favorite student before this? Was that you? No, it definitely wasn't you. Okay. So that was the crux of the lecture last time. We have Laplace's equation. It's easy to solve numerically. And it allows you to really get a nice picture of what's going on in field distribution. You'll see some really nice, pretty graphs in your homework assignment next that you turn in when you get back from spring break. It's not going to be due until the Thursday after spring break. So just for clarification. Yeah, so that's a takeaway. Now, boundary value problems are really interesting, and that's an interesting problem that you can kind of put in your back pocket and take away, play with on your own time if you want. I got really into modeling electrostatic problems when I was an undergraduate because I did a senior independent study with a professor in EMAG at Virginia Tech. His name was David DeWolf. Really neat guy, brilliant fellow. He was always renowned for solving the most complicated problem and trying to tackle the most complicated problem you could possibly think of in EMAG. You know, trying to analytically model waves as they pass over oblate spheroidal raindrops so that you can figure out, like, you know, link margins of satellites in a storm or something like that. You know, that's how crazy. He even looked like Einstein. He's this really, really kind old Jewish man. He's a Holocaust survivor. He's a really old fella. Brilliant guy. And he even kind of had the frizzled hair just like Einstein. So he's like one of my favorite all-time professors. He was on all my committees and everything. So I think he's like an emeritus professor over in Holland. That's where he came from. So he teaches there at Delft a little bit or does a little work on the side. So anyway, very brilliant guy. He just said, Greg, you know, we should do a study on electron optics, because he'd written a book on electron optics, which is basically the stuff how to make the cathode ray tube work, you know, how to make a beam and focus it and accelerate it and get it to be pinpoint at the place that you want it to strike. There's a beautiful application of electrostatics. And he was sort of the master. He had worked on that in RCA back in like the 60s and the 70s before he had become a professor. And so, man, I just drank from the fire hose and learned all this stuff about electrostatics. 2 solid semesters. We were doing finite element analysis, which is really similar to the thing that I drew over there, except instead of using square grids, you use kind of triangular grids. And it turns out you can actually formulate a way to solve that problem in any kind of coordinate system. So, you know, why on earth would you ever try to complicate your life by discretizing something other than a grid? So, let's say I had this boundary value problem. Let's say I had a piece of metal here that was being held at 100 volts. And a piece of metal here that was being held at negative 100 volts. And I was interested in looking at the fields in here, modeling maybe how an electron would interact with that area. And let's say the rest of this is just grounded. So where is the most interesting part of this solution? It's probably right here. This is where the steepest gradients are going to happen. This is where all the E fields are going to happen. And so the idea, if you ever hear the term, has anyone ever heard the term finite element before? Yeah, what is the context of you?
I think it was in the semiconductors class.
Ah, semiconductors class. Oh, cool. I wonder what they're using it for in there. There's so many uses. It's you see this come up a lot in mechanics, in stress analysis. You use a finite element algorithm to compute stresses in materials. You can use it for electrostatics too. The idea here is, okay, instead of making a fine grid, because if I make a fine grid across this entire structure, my precision that I need in the business zone, so to speak, is going to dictate the precision that I have to put everywhere. And if you think about it, I have a system here where I might have 1,000 by 1,000 grid points if I want a really accurate solution. That means 1,000,000 points that I have to solve voltage. And remember, they're all interdependent with one another. So effectively, that's like solving 1,000,000 equations with 1,000,000 unknowns. That's hard for even nowadays computers. So what you would rather do is just kind of sporadically put your points, bunch them up in the place of interest, and then kind of just like where you don't care about the precision of the problem too much, just kind of put them like that. And that's the idea behind finite elements. So you get this weird organic kind of triangular mesh. And it turns out that when you get through and you minimize the energy, which is really what that Laplace's equation is doing, you get something that's kind of, instead of just the node is the average of its neighbor, it just winds up being that a node is a weighted average of its neighbor. So, elegant little technique. Now there's another way to solve these problems. Some problems in this space, we won't cover this in this class too, but I have to always have to tell students about it because there's always like 2 or 3 budding mathematicians in the class that always want to go up and read more on this subject. But let's say this is going to blow your mind. This is just going to, it's Enrichment Thursday. Only half of you are here, so 2/3 of you are here. We'll play a little fun. This will blow your mind. So let's say you didn't want to use the numerical technique to solve your boundary value problem. Let's say you wanted to get you really like Dr. DeWolf and you thought that you had to get like a really nice analytical result out of it. Let's say you looked at a problem like this. You have a piece of metal and it's kept at 100 volts. And then you got a ground plane here, infinite ground plane, which is, of course, 0 volts. How does the field distribute in space? Well, this is something that we could kind of discretize and come up with a boundary value problem. We'd make the space really big, set this out to 0 on the edges here, maybe interpolate a little, either enlarge this so that it includes the corner, and then kind of interpolate from 100 volts to 0 volts in a steady manner down there. And this would effectively be our boundary. And then we could use that technique where you just average the nodes around and iterate the solution to something accurate. Well, this turns out this problem actually has an analytic solution, and there's only one way to get to it. There's a lot of problems like this that at first blush don't look like they have a simple solution. But they do if you apply something called the Schwarz-Christoffel transform. I know, doesn't that sound messed up? and it literally messes up the problem so that you can solve it. So get this. This will blow your mind. You identify line segments in your problems and points of transmission. So for example, this goes up to infinity. So this is line segment number 1, from infinity down to this point. This is line segment number 2, from this point to infinity. This is line segment number 3, from infinity to the other infinity over there. So you can see that really this is just 3 line segments if I take this point and kind of move it off to infinity, right? Kind of equivalent. Well, there's a special thing called a special field of mathematics called conformal mapping, which basically allows you to bend spaces, bend coordinate systems into other coordinate systems. So you perform the Schwarz-Christoffel transform, which is a type of coordinate map, which literally unfurls this problem so that your line segments look like this. And then this part is 100 volts. The node, it doesn't really matter where you put the node in at this point. And then this part is 0 volts. And it turns out this has a very simple analytic solution. If you apply Laplace's equation to this problem, you will actually get radial spokes that evenly go from 0, 10, 20, 30, 40, 50, up to 100 volts in even increments in angle. Then when you want the real solution, you can unbend it by reversing the conformal map, and all of a sudden you have this beautiful solution with equipotential lines that bend around like this. Isn't that messed up? And the whole secret is because the Schwarz-Christoffel transform is a special kind of transform. It is an angle-preserving transform. In other words, if I have two shapes that intersect with a certain angle between them, if I do the Schwarz-Christoffel transform the way that they define it, this angle will be preserved. I mean, the paths will still be messed up, but the angle will be preserved. And it turns out you can show that Laplace's equation is angle invariant through a conformal map. If you can solve a function with a Laplace transform or the Laplacian operator, say Laplace of this is equal to 0, then that equation will still hold if the conformal map is an angle-preserving transform. Things that you will never have to use in your life, but will be able to whip out at a dinner party and be really impressive, provided there are a lot of mathematicians and engineers at the dinner party. Yeah?
How did he discover that technique?
The Schwarz-Christoffel transform? Well, this was in the days when nobody had computers, so all you had to do was think about the problem. I wish I could turn many of you back to the 1920s or the 1800s when people were doing a lot of these calculus relationships, because you would be forced to think about the problem and not look up anything on Wikipedia or try to calculate it in a calculator or outsource your homework to a person in Taiwan. Oh, yes. Are you from Taiwan?
No.
Okay. You're from Taiwan. Okay. Sorry, I was trying to drum you guys up some business.
How is the transform angle preservative when the two-line segment become going from 90 to 180?
Yeah, so it has to do with the differential geometry employed here. This guy here, if you look really closely, like the in a very small increment of space, it will only kind of bend things around and twist
the
it.
line segment for the 100 volt.
This one here, yeah. So this is kind of a singularity. So because this is a corner, it's not preserved in the transform. But a line, the equipotential line that kind of snakes around continuously around that corner, that line, if you map like that and another continuous intersector, that angle would be preserved in the conformal mapping. Oh, yes.
What's the problem with changing that line segment into a different geometry? Like make it like a sphere, or does the boundary matters if you change the geometry of it?
I'm not familiar if there are some curved differential geometries. I'm sure they're out there. I've never worked with those before. This Schwarz-Christoffel transform is good for things like polygons and that sort of thing. So those are the type of problems that you see solved with it. Things like this, or sometimes like the microstrip problem, where you have an infinite ground plane and something sitting above that. If you actually want to model the fringing fields, I believe there's a Schwarz-Christoffel transform for that, because it's all line segments in the cross section. Any other questions? This will not be on the test, by the way. Yeah?
Are those two metal plates connected at infinity?
Like over here?
Yeah.
It doesn't really matter or not. It could be. I mean, if you have two metal plates that are at different potentials and they actually touch, if they electrically touch, they discharge across each other, right? But if you put, in a lot of these types of problems where you have, a plate at 100 volts and then another plate at 0 volts, there's an assumed a little dielectric bead or something keeping current from flowing from there to there. So it can look a little bit fishy looking to an electrical engineer who's used to circuit analysis. Say, wait a second, I got a 100 volt drop in 0 point in space. I've got infinite field right there. That's no good. It's going to end in a fiery arc. But, well, you put a little bit of gap there just to keep it honest, physically speaking. Yeah?
How did you determine where the endpoint, like say that ground plane, you just mark the point on 0 on that?
Oh, yeah. So you always make the discontinuity between 100 volts and 0 volts the origin, because then the geometry can be solved this way. Laplace's equation in cylindrical coordinates, you can show you can reach that solution with that. We may even work an example of that later. So anyway, I guess the point of the story is you have a nice basic set of quantities that allow you to relate field, voltage, charge. Laplace's equation kind of gave you your first insight into numerical modeling of more complicated scenarios. But if you wanted to, you spend the rest of your life studying this stuff. I'm not advocating you do that, but we're going to study in this class for the remaining lecture how to calculate capacitance, because that's a really nice parameter that we can use as electrical engineers. How do we define it, and how do we compute it? So let's go ahead and start doing that. Capacitance. What is it? What is it? Capacitance is kind of like voltage in the sense that it's always measured between 2 points in space, usually two conductors, because a conductor is at the same potential all around its structure. So for example, if I had a piece of metal like this, and I had another piece of metal like this, is what we like to call a PEC, perfect electric conductor. And then the next thing we do is we separate charge. We put plus Q charge over here and minus Q charge over here. The implication, of course, is that we took the electrons from here, and when they left positive charges that were equal and opposite to this, and we put those electrons over on this piece of metal. Well, it takes work to do that. It takes work to do that. And we could figure out the work that it took to do that by just looking at the scalar electric potential function between these two pieces of metal. So there will be, if we did a path integral of electric field, that was another trick in our arsenal. Let's see, let's make this A and this B to keep our sign consistent. If you add up the E field going from A to B in this system, you'll have had to have done some work on the system. And it turns out that the amount of charge that you separate for something like this, for a fixed geometry, for the amount of charge that you wind up separating, and the amount of voltage that you accumulate, the work that you have to do on the system, is always proportional. So if you double the charge, you'll double the voltage. They're always proportional to one another. That constant of proportionality is what we call the capacitance. capacitance in farads, and this is honest to goodness farads, not farads per meter that we talked about in transmission line theory. This is equal to the charge separation over the voltage. And that's the voltage between the two charges that you've separated. Of course, if these are perfect electric conductors, what will actually happen is that the positive charges will migrate to the edge, because you can't have E field inside the conductors. And that all of this will be basically at the same potential. So it wouldn't really matter where you took your path integral of electric field and accumulated the electric field. You'd always, in a proper universe, always get the same voltage V. So does that make sense? Well, that's a pretty straightforward definition. You probably learned something similar to that in physics too. Let's just test it out with some basic understanding of a problem that we should be familiar with. Then we'll work something a little more complicated. Let's look at the parallel plate capacitor. This is the kind of stuff that you're using in your electronics laboratory. It has epsilon in between there, some material that you've put in between two conductive plates. And for the sake of argument, we'll put positive charges up here and negative charges down here, a distance d separating the two, and if we wanted to, we could even make this nice and three-dimensional, like so sort of make this like width, depth. Actually, I probably got that backwards. Let's call this width, depth. Okay, so how would you field model this very simple problem based on our definition of capacitance? Well, if we look at the cross-section, let me just redraw it down here so that I don't mess up my graphical masterpiece above. I've got this minus rho sub s surface charge density at the bottom, and then an equal amount of charge. And for all intents and purposes, I'll assume that it's uniformly distributed. This is a plus rho sub s. That's a good assumption that it's equally distributed, because remember, charges are free to flow on a conductor. And so if it's...
No.
That's not right.
No.
That's not right. Don't go anywhere. We have 30 minutes. Okay, good. The bells are on break too. The charges tend to spread out because they're mobile on a piece of metal. And so if we look at this system, and so how do we go about modeling this? Well, like any good engineers, we're going to make assumptions. We're going to say these are really big plates compared to their separation distance d here. In fact, they're going to be so big we'll call it infinite. And then we'll kind of fudge the solution afterwards, right? So we've already solved the infinite planar charge problem in this class. What was the result? Does anybody remember? Did it equal Q? Well, what we found, if we had, like, say this was the origin.
Well, wasn't the E field just in the Z direction?
That's right. It was in the Z direction. You're exactly right. If it was above that plane, if it was below that plane, it was pointing the other direction. And do you remember the dependence on there? Yeah, that's it. Rho sub s. And And this is actually a minus. I put the minus at the bottom. So I got to put a minus rho sub s over 2 epsilon. Whatever material I put in there, I got to put that epsilon permittivity in the denominator. And we found that this was a constant. It was a constant. Regardless of where you were in height, or x or y. And this is true for even a finite parallel plate capacitor until you get towards the end, and then then the fields kind of bend off a little bit like that. But you don't have to worry about that. Let's just pretend it's infinite for a second. So this one points in the minus z direction because it's a negative charge, and that means that on the other side of the plate you'd have plus rho sub s 2 epsilon z hat. Up here, likewise, because you're on the plate, if I was above this plate, the same component, the same contribution to E field due to this negative rho sub s charge would still be present. It would be in the minus rho sub s 2 epsilon z. These are forces solely due to the presence of the bottom plate. At the top plate, we have the opposite thing. Remember, the E field is going to point above for the top infinite plate and below for below the plate. And so there's going to be plus rho sub s 2 epsilon z hat. And then beneath here, it will be minus rho sub s 2 epsilon z hat minus rho sub s 2 epsilon z hat. So I really have 3 distinct regions here. And notice that in 2 of them, my total field is 0. Nothing. Nothing. This is the only place where the polarities actually align such that you get a total field of rho sub s with a minus sign in front of it over epsilon in the z hat direction, the minus z hat direction. Does everybody understand how I got there? I didn't have to use any Coulomb's law. I was just picking out of the pocket the problem that we worked about 2 weeks ago. And I got nothing up here. So now, I need to go back to my definition. Capacitance is equal to charge separation, total charge separation in coulombs, not coulombs per meter squared like I've got it over there, divided by the voltage. So let's go figure out what is that for this problem. Well, the voltage is going to be the integration of my E field from the top plate to the bottom plate with a minus sign in front of it, right? Voltage from bottom to top is going to be the integral, let's call it from 0 to d. It's going to be in the z direction, so my dl unit element of integration is actually going to be dz in the z hat direction. I'm integrating up, counting the contributions of E field along a z hat path. And my E field here is rho sub s epsilon with a minus sign in front of it, and that's also in the z direction. Conveniently, the z's dot out with one another, z dotted with itself as 1, and so this integral really reads dz prime times this constant. Trivial to integrate. Oh, I got to put a minus sign in front of there too, right? Because E field is always minus the gradient of voltage. Voltage is minus the path integral of E field. So what I wind up with is rho sub s times d over epsilon. That's the first half. That's the voltage between the 2 plates. What is the total charge on this system? Well, it's going to depend on how big the plates are. If I've got minus rho sub s here and plus rho sub s here, then the total charge that was separated is actually d times w times my surface charge density. Capital D, d times w, or the area of that plate. Let's just use area. Area A times rho sub s. Meters squared times coulombs per meter squared. And so our final answer, let me write it over here so we have a clean result. For the parallel plate capacitor, with area A and separation distance d, capacitance is equal to the total charge, which we said was area times rho sub s, divided by the total voltage, which we said was rho sub s d over epsilon. Rho sub s's cancel, as they should, because this result should be independent of the charge density. And what you get is epsilon times the area divided by separation distance. Of course, that's the formula that you probably learned in physics, right? Parallel plate capacitor formula. We use it all the time in electrical engineering. Let me give you an example. Well, let me change the subject. How do we realize this? How do we build a capacitor in electrical engineering? And so you pick it out of the bin, right, at your electronics lab. How did they build it? Well, they did this exact same thing. They picked a piece of metal, and they took another piece of metal, and they put it together. Usually, for those cheapy capacitors that you're using in 3041 or 3042, they're just paper dielectric. So the epsilon is not very large. Epsilon is like, I don't know, 1 point something. You'll be lucky to get 2. Maybe some of them use some plastic, some Teflon or some polypropylene or anything that insulates that you can make really thin. And you take those 2 plates and you press it over. And how do you beef up the capacitance? What are all the ways that we can beef up the capacitance in this problem? Because capacitance is a pretty valuable thing. Like in power supplies, we'd love to have, a farad capacitor. It's actually hard to build one of those, though.
Bigger area?
Bigger area. Well, you can only make the thing so big. So what do we do if we want a lot of capacitance in there? Yeah, we got to change the epsilon. We got to decrease the distance d, or find a way to increase the area. So here's the different ways that we electrical engineers realize this in practice. First of all, the easiest thing to do, because these things are made out of paper, you can only get so thin, right? And what's more, paper is like, I think it's mostly air. Air is a terrible dielectric. So you don't really want to make super, super thin paper. And so the cheapest way to get the capacitance up is to just make a really big area and then roll it up like that. So that makes the area really big. That's one way to make the area big and to increase capacitance. There's another type of way to increase that, and that's to get this d really small. And so you can't really... You can't really make paper that thin, so there's another technique used in electrolytic capacitors. And electrolytic capacitors look like really crummy capacitors when they first come off the assembly line. You make some parallel plates. In fact, they don't even look like capacitors. They look like resistors. Because what you do, you got 2 pieces of metal, and you've got a solution in here, an electrolyte solution, water with some stuff dissolved in it. And that tends to conduct. And so what they'll do is they'll hit this with an initial DC voltage off the line, and that will deposit a thin layer of insulating material as the electrolytes come out of solution. And this D is very thin. It's much thinner than what you would get if you just used a piece of paper. And so because the rest of this solution conducts, it's actually like moving the metal all the way to the edge of that D. And so that's how you get even bigger values of capacitance. Of course, what that also means is that you got to observe the little plus and minus sign on the electrolytic capacitor, right? Once you pull it in one direction, you got to keep using it in the particular polarity that's assigned to the cap. If you reverse that voltage, what you'll do is you'll dissolve some of this electrolyte potentially that's come out of solution. It will no longer act like an insulator. And in fact, in some instances, you will start to send a lot of current through your water, heat it up, and pop. In a puff of steam, your electronics project ceases to function. How many people have ever seen this happen? How many people have done this in your laboratory? Okay, good, good. I tell you, maybe this doesn't speak kindly to Virginia Tech students where I came from. But I started out as an electronics TA my first year in grad school. And I had to do all the equivalent of 3041 there. And one of our labs involved a little power experiment where you had to rectify power and then use an electrolytic cap to kind of smooth out the ripple. I don't know if you've ever done anything like that in one of your electronics experiments. But so I gave this lecture very clearly. There's a plus sign and a minus sign on the electrolytic cap. Put the positive voltage on the plus side and the negative on the minus sign. Don't switch it, or else it's going to explode. I gave that lecture at the beginning of every class. Statistically, it was like 50-50. 50% of the projects blew up because they put the capacitors in. It's like you weren't even listening. I could have given those instructions to Stevie Wonder, and they would have turned out exactly the same way. Right? But I trust your Georgia Tech students, you wouldn't do that. You would not have 50% failure rate in an experiment like that. I can bust on that to the students because I was from Virginia Tech. But it's like any place. You get some really bright students in the undergrad place and other people that are kind of just finding their way and they don't really want to engage themselves. I did have one guy once in my electronics lab. He was hooking a circuit together and he was staring at the wire and his alligator clip. And he turned to me and he said, does the clip have to touch the metal part or can you just put it on the plastic part? I said, at the frequencies you're working at, it needs to go on the metal part. True story, sad to say. So yeah, that's how you make an electrolytic capacitor. Now, another way to increase the capacitance. We talked a little bit about epsilon. There are actually some really interesting engineered materials that can give you super high epsilons, things like ceramics. Barium titanate is one that I think some of my chemistry colleagues have played around with. And this has epsilon R's of like 60s, 100 something. It depends on how you manufacture it. But it's a very high permittivity substrate. In fact, there are even some epsilons that can go really high if there are a couple ways to do this. First of all, there are these super caps, right? Anybody ever used a super cap before? Do you know how they make them? No? They're just super, right? They're just super. No. So what they do here is something kind of like the electrolytic capacitor, but they take an aerogel. An aerogel is like, if you look at YouTube videos, there's this puffy mass that like would literally almost float off your hand if you just shook it a little bit, because it's a very light network of fibers. Super light. It was something that came out of the aerospace industry originally. Something that had extraordinarily high structural integrity per unit gram of substance. So extremely light, but it holds its shape. And then the idea here is that you metallize these. You dip this in a metallizing solution, put a coat of metal on here, dip it in something like an electrolytic solution, and again you put a layer of insulation around the fibers. And now you've got an electrolytic capacitor, except instead of the area being 2 plates, it's now the entire surface area of the uncountable number of fibers in the aerogel. And so it winds up being many, many orders of magnitude larger than just a little plate that you put in a comparable cross-sectional space. And so your capacitance goes way up. Way up. So if you ever see the term supercapacitor, they're probably playing some trick like this with the innards to give it a super high value of capacitance in a very small area of space. It's okay. Let's keep going. Let's see if we have time to finish this one off. We have this device that we studied at the beginning of the term called a coaxial cable. So now let's take it back to transmission line theory. What is the per unit length capacitance of coax? Remember the formula here? Or the formulation, I should say? Radius A is your inner conductor. There's a radius B as your outer conductor. And there's some sort of dielectric inside epsilon. So I'm going to use a little Gauss's law here to figure out the E field around this thing. Remember what Gauss's law says? It's what's inside that counts. And so what is the E field going to be in this situation? Well, here's what I'm going to do with my charge separation. I'm going to put rho sub s, a surface charge, all along the inside. And presumably, I'm going to call it, let's call this rho sub SA, because that's going to be on my inner radius. I'm going to put positive charges in there. The positive charges are going to evenly spread out around the conductor, because charges don't like to bunch up next to one another. They have the freedom to move in the conductor. And that means there's going to be an equal number of negative charges when you add them all up on this outer conductor. But I'm not going to really bother with that. This is going to be minus rho sub SB, and because the geometry is different, it's not going to be the same spatial density. But it turns out it's not going to matter, because I'm going to do my Gauss's law integral inside, because it's what's inside that counts. And so what I find, looking at this problem, my E field as a function of, well, this is a cylindrical structure, so let's work it in cylindrical coordinates. E field as a function of rho, phi, and z. This is a semi-infinite coaxial line. Z is in this direction. I'm going to say this is z independent. So I'm not going to write a z. In fact, this also has radial symmetry. Remember, phi is measured about the z-axis in this direction. The radial direction is not going to matter either. The only thing that should matter is how far I am away from that radius. So already, with just that simple argument of symmetry, I can write this as my full electric field solution should only be a function of rho in terms of its point of observation. Everybody agree with that? Yes? Okay, good. Because we were going to fight if you didn't. Okay. And now, we also can probably tell that that E field component at that position of observation rho is going to point in the rho hat direction. It's not going to point in phi, it's not going to point in z, because that would kind of destroy the symmetry of our problem. The charge is here, so of course, that E field is going to point outward in the rho direction. There should be just enough charge down the line here to cancel any lateral component that the charge down this side of the line should produce. So it should always point away from the structure. So this, I can write this as E sub rho as a function of rho in the rho hat direction. That further simplification. There will only be a rho component, and it will only depend on rho. Now, the whole reason why I do these kind of simplifying arguments is because, as you know, as we've shown earlier in the class, when you do approach a Gauss's law type problem for these symmetrical problems, you can often just do the integration in your head without actually writing it down. You can just use geometry to solve the integral, and that's ultimately what we want to do in this class. We don't have to be 7th level calculus masters. So let's figure out how to do this. I'm in a material that has epsilon dielectric permittivity. So my D field within that area is going to be equal to epsilon E rho as a function of rho. Stick it on the rho hat. Gauss's law says my surface integral of D dotted into the surface normal around an enclosing volume. Let's write it this way. Keep the mathematicians happy. Enclosing surface is equal to enclosed charge. So the surface that I'm going to pick is a cylinder centered on the z-axis that includes my first conductor but not my second conductor. It will be a point rho away from the z-axis. And it really has 3 sides, right? It's like a Pringles can. It's got the curvy outside and then the 2 circular ends. And if I integrate across all of those ends and the circular side, the curvy side, then I should get my total flux, electric flux through the volume, and that should be equal to the total charge inside. So let's take a look at this. So really it's end 1 integral plus end 2 integral plus curved side integral. These are easy to evaluate because they are 0. The surface normal for this end is in the minus z direction. The surface normal for this other end, wherever we choose to draw it, d units down the line, say, is in the plus z direction. If I dot that with my D field, as I always have to do in my integral, my surface normal element of integration, z dotted with rho is always 0. They're always perpendicular, no matter what point of observation you're looking at. Make sense? Well, that's good. That simplifies our life. And if we're doing the side, the surface normal is always rho hat, which always perfectly aligns with my electric flux density that I've assumed in this problem. So I have a rho hat dotted into something that's going to be in rho hat. So in this case, the full amplitude of my electric flux density contributes to this integral. All I really have to do is just take this value and multiply it by the surface area of that cylinder. Because that surface area is all at the same rho. Rho is going to be a constant in that integration. I'm integrating along z. I'm integrating around in phi, in azimuth. I don't need to vary my rho. So I can treat it like this all like a constant. So if I have a cylinder of length d and radius rho, what is the total area around that cylinder?
2 pi rho d.
Oh, yeah, good. Good job. 2 pi rho times d is the total area. I'm integrating this thing, which looks like a constant over there, epsilon e sub rho, the rho component of e, is a function of rho. And that should be equal to enclosed charge. Well, my enclosed charge is really, I just have a little cylinder of charge in there with a surface charge rho sub SA. Well, that should be easy, right? I just use the same cylinder formula. 2 pi, this time my radius is A times D. And it's rho sub SA. So let's see. Yeah, this is good. 2 pi's cancel. D's cancel. And what you get is I gotta finish this problem up quick. Rearranging E as a function of rho, the rho component of the E field, is equal to A, surface charge density, rho sub SA, divided by the distance away from that z-axis that I'm observing, divided by epsilon. If I want to integrate this to get voltage, voltage is minus, I'm going to integrate from A to B. And I'm going to do it along the rho component. So here, let's do this real quick. This is a constant, this is a constant, this is a constant. This is in the rho hat direction. And I'm integrating from A to B, which is the rho hat direction, d rho. And so what I get, here's a minus sign there. Constant, constant, constant. This is 1. I just have the integral of d rho over rho from A to B. We recognize that instantly as the natural log of B over A. So that's my voltage between the 2 points. What is my total charge? We already calculated it. We said it was 2 pi A rho sub S times D for the charge separation. What is my capacitance? My capacitance is defined as the total charge over the voltage between those points when that total charge is separated. Dividing through, we see that this is going to be, let's see, minus 2 pi A rho sub S times D over minus A rho sub SA over epsilon times log B over A. A's cancel. Rho sub SA's cancel. We only have seconds before the bell rings. 2 pi D. I'm going to flip my epsilon up into the numerator. And I'm going to keep here log B over A. And for some reason, I picked up a minus sign. How did that happen? Oh, my voltage. Oh, you're right. You're right. My voltage is negative. Flip it. Let's get the polarity right. So then I get this. This is the capacitance of a coax of length D with radius, inner radius A, outer radius B. And of course, if I want the per unit length capacitance, I just need to divide out by the length. And lo and behold, look at that. This is the exact same formula we learned the very first week of class when we were studying transmission lines. You now have enough knowledge up here to calculate that. In fact, obviously, they wouldn't be nice and contrived for most typical transmission lines, but you have the capacity to at least set up the problem for a transmission line of any complexity. So your homework number 9, which will be due 2 Thursdays from now, actually just does some field mapping and some field analysis using the numerical code that I give you, so you don't have to write it yourself, but explore some of the more complicated topologies of these other types of transmission lines. Not just coaxes, but microstrips and strip lines. And so have a great spring break, and I will see you in a couple weeks.